The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. Welcome to Measure's monthly webinar series. Today's topic is application of symmetrical components in relay testing. Hopefully you can all hear us all right. If you can't, I recommend using the audio on your phone rather than your computer. Sometimes that helps out. My name is Jamie Smith, and I'm the digital marketing specialist for Measure North America, and I'll be acting as the moderator for today's presentation. I'll be supporting you on any technical issues or questions for our presenter during the session, so feel free to ask any questions. Most likely we'll be answering any of those questions towards the end. After the webinar, we have a 30-minute segment set up. On the right side of your screen, you'll see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment. Everyone that has registered for this webinar will receive a copy of the presentation afterwards and a link to the recorded session if you want to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and we'll try to answer them as we have time. Today, our presenter is Mohit Sharma, and he's the application engineer for Relay Products. He's based out of our Dallas office. Thank you for joining us, Mohit.
Thanks, Jamie, for the introduction. So let's start the presentation with, let me give you an overview of the presentation, what we will talk about. So we will start with what are basically symmetrical components, what are their importance, and what exactly it is, and a little bit mathematics behind that. Then we will go to the applications of that symmetrical components in relay protection functions, how we can apply those components in the functions. And then we will check that how we can use that knowledge of symmetrical components in testing some of the protective functions. And at the end, conclusions. So before going on to the presentation, let me show you a picture. So this picture, you can see that it has a substation fire caused by probably by relay settings fault, improper relay settings. So you can see how damage this is causing to the substation. Now you would be asking, okay, how does the image relate to this webinar? Why is the presenter showing this image to us? I showed that image because, as I said, that fire was caused because of improper relay settings. And you do the relay settings after you do the correct fault analysis. In order for you to do the correct fault analysis, you need to have the knowledge of sequence components or symmetrical components. So in that way, you can protect your system. So you can see the importance of the knowledge of symmetrical components in power system industry. Next, in order for us to understand the concept of symmetrical components, let's first know what a balanced and an unbalanced system is. So I'll start with a balanced system. So on the right, you can see that we have a vector. So all the vectors are equal in magnitude and equal in phase angles apart. So this could be a voltage vector, this could be a current vector. So this is kind of a system, it's called as balanced system. Examples of balanced system, a three-phase fault or a three-phase load, a balanced load. So in these conditions, you will have a balanced system. As you can see, this is a symmetrical system because of the symmetry associated with the magnitude and phase angle. So we can call a balanced system a symmetrical system as well. Now let's talk about unbalanced system. You can clearly see in the picture on the right that all the magnitudes are different, all the phase angles are different for voltage and current. So it's pretty hard for an analysis guy or analysis expert to study the whole power system with these unbalanced scenario, because you cannot reduce to the right kind of fault, things like that. So the examples of unbalanced system would be a single line to ground fault, phase to phase fault, double phase to ground fault, which is phase to ground, open pole condition, or an unbalanced load. So these all conditions will give you an idea of the unbalance. It will tell you that, okay, this my unbalanced system is existing. And you can see the asymmetry in the vector diagram, so that's why people call unbalanced system as asymmetrical system as well. The reason I showed you unbalanced system is because the whole concept of symmetrical components lie besides the idea of unbalanced system. So let's now let's talk about sequence components or symmetrical components. At the beginning, I would like to know a little bit of history behind symmetrical components. So back in 1918, Charles Fortescue, actually he was working on the operation of induction motors under unbalanced condition. So he saw that in any unbalanced vector, I can actually remove the problem of doing the analysis by making it a combination of symmetrical system. So what he did was, let's say he was having an unbalanced system like this. So according to his theory, he said that this unbalanced system could be resolved into three symmetrical vectors, you can see, and he called them as positive sequence, negative sequence, and zero sequence. Let me little bit explain you more detail about this. So an unbalanced system is having different magnitudes and phase angles. So we are unable to do the proper analysis of that. So if we resolve this into these three vectors, which are balanced, which means they are equal in magnitude and phase angles, I can get a resultant like the unbalanced vector. So now I have a theory and an idea of doing the analysis for an unbalanced system. Again, he clearly stated that the whole concept of sequence components is theoretical and mathematical, so it's not physically existent. So just keep in mind that it's all theory and mathematics, just to make people understand that how an unbalanced system looks like. Okay, let's talk about a system like this. So we take voltages from the PTs, we take currents from the CTs. So I have the known quantities, which is my phase A voltage, B voltage, C voltage. I have my known current quantities, which are my phase A, B, and C. So he said that in any unbalanced system, as I explained, this is, let's say, this is an unbalanced system when I have different magnitudes and phase angles associated with them. So according to him, we can resolve it into symmetrical and balanced systems. So this is how it did. So let's take, for example, this is my unbalanced system. I have my phase A voltage, phase B voltage, and phase C voltage, and it's all unbalanced. So let's make some addition of the positive, negative, and zero sequence in order to get this unbalanced system. So as you can see, let's start with the phase A voltage. So phase A voltage, as I said, is a combination of all the three sequence vectors. So this is my positive sequence vector for A phase, negative sequence vector for A phase, and my zero sequence vector for A phase. So if you sum all of them together like a vector sum, I will get my vector VA, which is my voltage basically. But as I said, VA is our known quantity, and we are supposed to compute the sequence quantities. So we will explain that in the further slides, that how we can deduce the functions of VA1, VA0, and VA2 from the VA. So again, with the VB vector, it's going to be the same thing. It will be a vector sum of your positive sequence, negative sequence, and zero sequence. Same goes with VC, positive, negative, and zero sequence. So I've made this diagram. As you can clearly see, each vector is parallel with this one. So it's quite understandable that what exactly is happening. Okay, now let's talk about a little bit of mathematics, that what exactly we did in the previous slide. According to Charles Fortescue, because this whole theory was derived by him, he said that I can have three different symmetrical vectors to have an unbalanced system, right? So and he said them as positive sequence, negative, and zero sequence. So now let's talk about what exactly are they and a little bit of physical significance, where they will be present, things like that. So positive sequence, as you can see, it's nothing but a vector which will be there for a balanced system. And I'm assuming my system rotation to be ABC, which means my positive sequence vector would be exactly like my system vector. So I have ABC as my rotation. On the other hand, my negative sequence is nothing but a positive sequence with a reverse rotation, which means if I have a system rotation of ABC, I will have my negative sequence vector as ACB. But they all are equal in magnitude, as I said. And then I have zero sequence vector, which does not have any kind of rotation, and they are all same in phase angle and equal in magnitude. So if I sum all of them together, I'm going to get my unbalanced vectors, as it is derived in the equation which you can see here. My phase vectors are equal to my summation of all the sequence vectors. Just to give you a little bit of idea about zero sequence vector, but we will cover that in my further slides. Just remember that the zero sequence vector will be caused because of any ground fault. I mean, any current flowing through the neutral of a system. Just keep that in mind, and we will talk about that in detail in the later slides. Okay. But there's a problem we have here. As I said, VA, VB, and VC are the known variables. We know them from the PTs. We are measuring them for the power system. But we don't know these 6 quantities. So I have 3 equations, but I have 6 variables, which means I cannot solve this equation, all these equations. I need to have my variables in which is exactly in the same number as my equations. So I need to reduce this VB1 in terms of VA1. So all these 6 vectors here should be in terms of these 3 vectors. So what he suggested was, okay, let's take a concept of A operator. According to him, the A operator would be nothing but a vector. If you rotate it in the counterclockwise direction by 120 degree, keeping the magnitude as constant, you will get the other vector. It's clearly visible here that if I have a VA2 and if I rotate it in the counterclockwise direction, I will get my VB2, my B phase vector, and it will be my A times, as I said, it's called as A operator, VA2. So VA2 is nothing, VB2 is nothing but VA2 angle 120 degrees. So in this way, basically his idea was to reduce my VB2 in terms of VA2. Now from the equation, it's clearly visible that I have a proper relation. And similarly, VC2 will be just 240 degrees apart. In the mathematics that we saw in the A operator stream, now we can say that I have my VB1 vector to be this, and I have reduced the whole equations in this format. Now in this equation I have 3 variables and 3 equations, so I can have a solution. So in that solution I will be getting all the sequence component values, and from that I can get any value I want. So these are the final equations that comes out when you do the inverse of the matrix. This is for the voltage and this is for the current. So you have all these 3 variables equations at the very end in terms of the known variables. Okay, now we have got a good understanding of how the mathematics behind the symmetrical components work. So now I know what exactly it is. Then I can talk about using this symmetrical components in some of the relay applications. But before that, let me give you a good idea about when and where my symmetrical components will be present in the system when a different kind of a condition is there. So taking an example of face-to-face fault, face-to-face fault will have a positive sequence component, negative sequence component, but not a zero sequence component. I told you to keep in mind that zero sequence component is the one that flows through the neutral. So a face-to-face fault will not have any current flowing through the neutral. So that's why it doesn't have any zero sequence component. Taking an example of single line to ground fault, I will have all these 3 vectors because now I have a ground current flowing, and that's why I can say a zero sequence component will be present. A 3-phase fault will just have a positive sequence component, or you can say it's nothing but a balanced system. And as I clearly told you that a balanced system is exactly what a positive sequence component is, just a mathematical way of telling that. Let's now go to the applications part. Open pole means your pole for the 3-phase, it will be getting opened. So it means that if you're having a recloser, so it has an opening in the single phase. Now let's go to the applications part. So let me start with the motor protection. The symmetrical component theory is applicable in the whole power system. So you take motor, you take generator, transformer, transmission lines, distribution system, you say it anything, it's present everywhere. But we will talk about some of them. So starting with the motor protection. In motor protection, you can use the negative sequence component to detect your phase-to-phase faults, phase reversals, single phasings, single and motor unbalance. Why we can use that? Because as I said, the negative sequence component is used to distinguish between a phase-to-phase fault and a 3-phase fault or line-to-ground fault. And it is associated with the reversal of the system rotation. So if I have a phase reversal, I can say it with the help of negative sequence vector. Let's take an example of current unbalance. So before the concept of negative sequence, all the sequence components came into picture, many people saw that if an unbalance of current occurs in a motor or a generator, there was an increased amount of rotor heating. And because of that rotor heating, there were mechanical vibrations and torque. But nobody was able to identify the cause, why, and nobody was theoretically able to explain what current unbalance, why it is having this kind of current unbalance, and why are we having vibrations and torque because of that. And one more thing I would like to say is the current unbalance scenario was created and it was against the nominal thermal curves of the equipment. So it was not following the nominal thermal curves, so that's why it was having a lot amount of heating beyond the curves, so it was very dangerous to the system. But with the idea of sequence components, now people can easily think of the motor unbalance or a current generator unbalance of current concept, why it is mathematically happening. So I'm taking an example of Multilin GE relay 469, which is a motor protection relay. According to the logic of sequence components, that we can say that negative sequence component will be creating a rotating magnetic field in the opposite direction. And because of that opposite direction rotating magnetic field, people studied and did a lot of analysis and found that it was having double the frequency. Because of double the frequency, you're having an increased skin effect in the rotor. You're having a high amount of skin effect in the rotor, and because of the skin effect, you're increased rotor resistance. Your resistance of the rotor is increased, and that's the primarily cause of heating in the rotor. So from idea of negative sequence, they can think of the current unbalance problem. Okay, now I can mathematically think of what is happening. I can justify that. In the relay GE Multilin 469, according to the relay logic, it says the setting of unbalance. Basically, it's nothing but it's directly proportional to the ratio of negative sequence to positive sequence current. So if, let's bring Mr. X here, for example, and he is a technician right now, and he doesn't know about sequence components, and he was given task to test Multilin 469 unbalanced function. So he went out in the field, he grabs the relay, he starts testing that, but he's uninformed about sequence component theory. So what he does is he just applies the phase currents, and it mistakes it for the sequence component. So he observes a pickup, but it was not exactly the pickup of the element. So it was a fail of the element. So he gets frustrated, and he spends more time on thinking why my relay is getting failed on that element. But if he had known the concept of sequence components, he could have directly applied the negative sequence current and get the proper setting, get the proper testing done, and a pass to the test. So now you see the importance of knowledge of sequence components. That's how it works out in the field. Another example, let's talk about negative sequence time over current. We all have seen the normal phase time over current curves and how they are being applied to protect the system from overcurrent conditions. But now we can see the concept of negative sequence since we know them, what exactly they are. And as I said before, that negative sequence is more sensitive for phase-to-phase faults because it distinguishes the system from other faults, right? So if you're having a phase overcurrent and a negative sequence overcurrent, I can have a clear distinguish in the negative sequence element for phase-to-phase faults, which means if I have a three-phase fault, my element will not get picked up, and I can have a proper distinguish between them. Some of the relay manufacturers, they are trying to implement the concept in their relays, and they are having a separate element for that. Just remember, a separate element than the phase overcurrent. So they do they basically employs the logic like this, and what they do is now they do some mathematics in the relay internally, and they come to 3I2 figure. My I2 is nothing but my negative sequence. And then they say that my 3I2 is the negative sequence overcurrent element pickup. So let's take this for an example to have a good understanding of what I'm saying. I have a system like this. I have a line recloser. I have a feeder breaker, feeder relay, which has both phase overcurrent elements and negative sequence overcurrent elements. Okay. Let's say I have a fault here, which is beyond the line recloser. So according to the concept, my line recloser should open to clear the fault, and it will follow this downstream phase time overcurrent curve because it's in the downstream. So my line recloser should open and it will clear the fault, but what if my line recloser fails to open? In that case, I should have a backup. I should have a backup to clear the fault. So this is an example of a backup. So usually traditional ways of having the backup protection is you just have a phase time overcurrent element of this feeder relay giving operation to the breaker to trip it in case of backup or in case of line recloser getting failed to open. So this upstream phase time overcurrent will follow this curve. Okay, now let's talk about a case where I have a negative sequence time overcurrent giving an open breaker command. So negative sequence time overcurrent, as I said, some of the relay manufacturers are employing the use of negative sequence component for line-to-line faults. Just for your assumption, this was I'm assuming this as a line-to-line fault. For a line-to-line fault, you will see when you do the fault analysis, you will see that my negative sequence element pickup is √3 times my equivalent phase pickup. So they have introduced the concept of equivalent phase pickup, many relay manufacturers, and then they incorporated in the relay, they incorporated the curves associated with equivalent phase pickup in the relay. And when you do a √3 times of that, you get a curve which is below the upstream phase over current. So it's clearly visible now that my negative sequence curve is more sensitive towards line-to-line fault. As I said, it's only happening in case of line-to-line faults. And it's more sensitive towards line-to-line faults. So I can say, okay, I can use this element for just to have more sensitivity. Now we have talked about motor. Let's see how this sequence component theory is in transformer. I've taken a classic example of transformer differential, and this is how my system looks like. It's a generator. I have CTs connected, which are Y connected, and I have a transformer, a delta Y transformer, and I have an 87 element which is observing the differential current from these two CTs. So in case of a high differential current, I mean an internal fault, my 87 element will pick up and I have a differential trip. And because from the differential protection, basically I'm protecting my transformer because it's a huge asset and it costs a lot. But in this scenario, there is a catch. As I said that transformer differential protection is only for internal faults. By internal, I meant that between these two CTs, if any fault happens, I will protect and I will trip the breaker, transformer breaker. But what if I have an external fault? So in an external fault, and let's say it's a line to ground fault. So in case of a line to ground fault, I would not want my transformer to trip because it's an external fault. It's not a fault which just happened in this zone. So I don't want my transformer to trip. But with this winding configuration, you will see that the transformer can trip. it will be tripping in case of a high magnitude line to ground faults externally. How? Let me show you. We talked about the concept of zero sequence, negative sequence and positive sequence. And I told you multiple times that zeros, remember zero sequence is associated with line to ground faults because it's a neutral current flowing. Clearly you can see that this network has a delta winding and delta winding does not have a neutral here. So there is no flow of zero sequence current in this circuit. But in this circuit, I have a solidly grounded Y in both my transformer secondary and my CT. So with this, I can have a zero sequence current flowing in my secondary loop. So there is no current here, but there is current here, which means there might be a differential current that could trip the transformer. So I need to eliminate the zero sequence. So if you haven't known the concept of zero sequence, all the sequence components, you would never have imagined what is happening in case of external faults for a delta Y transformer. Why the transformer is getting tripped. So now you know the idea of symmetrical components, and now you know that I have my zero sequence current flowing. Okay, so now you would think that is there a way that I can eliminate that zero sequence current flow to not trip my transformer for external faults? Yes, there is a way. So there are two ways. So the one way was the traditional way, which was employed in a lot of electromechanical relays before microprocessor relays came into existence. The first one was it's called as an external compensation. So basically in the external compensation, what you're doing is you're having a Y connected CTs to the side of a delta transformer, and you're having a delta connected CT to the side of a Y transformer, Y side of the transformer, sorry. So you have Y grounded on both the sides. This Y is grounded here, solidly grounded, and this Y is grounded here. So in both the loops, now I have zero sequence current flowing. So in a way, I have restricted my differential element to trip for external faults, because now I have equal current and there is no differential current flowing. But nowadays we have new microprocessor relays, a lot of numerical relays, which does not require changing the CT connections that I shown here to this kind of a configuration. What I'm trying to say is, even if you have Y connected CTs on both sides in a case for delta Y transformer, I can still compensate that phase difference. So many of the microprocessor relays, they employ the concept like explained here. Let me give you a brief idea about what it is. So you can see I have a delta Y winding, and my Y connected winding is 30 degree in difference. It's lagging 30 degree with the delta connected winding. So the microprocessor relays, they have introduced a concept of saying that, okay, if I have a 30 degree difference, why don't I say it to be 1? Let's say 1. 1 means an angle shift of 30 degrees. So with this CTC component, this basically I have taken it from a Schweitzer relay. So the CTC means CT compensation. So the CT compensation, what you're doing is you're rotating this Y winding in the reference phase. So basically you're compensating the 30 degree phase shift. So that if I say 1, so my relay will understand that I have to internally rotate my Y winding of the CT to be in phase with the delta winding. So if you put the settings like this, the relay will understand automatically, and it will overcompensate for the phase shifts. And in a way of doing the compensation for the phase shifts, you are also eliminating your zero sequence. That is done you can clearly see mathematically, but I'm not shown here, but mathematically it's visible. We have covered transformer differential, we have covered current unbalance in motor and generator. Now let's talk about generator protection and loss of relaying potential function in generator. Most of the relays, most of the generators have loss of relaying potential protection. What it is basically it is protecting your system from, in case, not protecting basically, it's the idea behind employing the use of loss of relaying potential is it is detecting the blowing of fuses which are connected in the PT secondary, and that PT is actually measuring your terminal voltage. So if my PTs are connected and they're measuring the terminal voltage of a generator and the secondary of it gets failed, then there is no relaying potential because PT secondary is giving voltage to the relay. And if there is no voltage to the relay, so this function will get activated and it will block my voltage related protective functions in the generator. So now it will block, and why it is doing the blocking? Some functions do blocking, some trip, depends on manufacturers. I'm taking an example of blocking of those functions. Why it is blocking? So the reason behind it is I don't want a false trip for a blowing of fuses in the PT secondary. In case of that, I don't want my relay to get a false trip. That's why I block those elements only for the instance of fuse failure. So, and I have an indication in the relay which says I have a loss of relaying potential. And now I can go and I can go to the field and I can change my fuses. So in a way, it is doing that idea. So many of the relay manufacturers, they employ that I have a relaying potential loss and I can derive the logic for that with the positive sequence voltage only. So when I have a decrease in my positive sequence voltage, I can declare a loss of relaying potential. You must be asking a question, why not a phase voltage? Why not a decrease in phase voltage? As I said, loss of relaying potential is clearly to detect your blown fuses in the PT secondary or any open circuit in the PT secondary. So in that case of condition, I want a discrimination between phase faults or unbalanced system and detection of and fuse failure. If I have a phase voltage, then I might think I might go for faults, and it will take a long time for me to think that, oh, okay, my fuses have gone wrong there. But if I have this function as the logic for positive sequence voltage, I can say that, oh, if I have a loss of relaying potential, I'll directly go and change my fuses, and there is no need to think of that, nothing like that. So let's bring back Mr. X again. Now he got a promotion. He is a settings engineer now. So what he does, but he is still uninformed about the idea of symmetrical components. So what he does is he goes and he sets the loss of relaying potential according to the phase voltage and doesn't realize the discrimination. He sees that there is the protection scheme afterwards is failing. There is a lot of problems in the protection scheme because of that. But if he had known the concept of positive sequence voltage, then he would have given a system a good look as from the protection scheme idea. So there's a huge requirement of getting the knowledge of sequence components. Now we have talked about all the different applications. Let's see the testing part and how we can use those components in the testing different protective functions in a way to simplify my testing. Let's take current unbalanced pickup in a motor or in a generator again as an example. So according to the relay settings, CT secondary full load amps, I'm assuming it to be 5 amps at the moment, just I'm taking an example. And I'm saying that my percentage unbalance is set to be 20%. So by 20%, it's not, as I again said, it's not related with my phase currents. It is related with my negative sequence current. So if you take 20% of 5 amps, the full load amps, you will get 1 amp, which is 1 amp of negative sequence current. So I'm saying my negative sequence current is my unbalance, to make it more clear. So what is happening is I have a system which was balanced before, and it was having full load current flowing through it, and I saw a 5 amp current flowing through the system, and it's a balanced system. And on the top of that, I saw an unbalance, and which has a magnitude of 1 amp, and as I told you, it's a negative sequence, so it will be having a different phase rotation. So from the color code, you can clearly see the negative sequence has a different rotation, positive sequence in compared to the positive sequence. So basically, you are imposing the negative sequence vector on the top of positive sequence, the balance system, in order to create an unbalance. So many software nowadays, they have software for the testing of relays. They have sequence component window, and you can just type in your sequence component values in here, and you can just go and see what my actual phasor values would be. So the software automatically calculates all the mathematics behind sequence, this whole concept that I showed you in previous slides. But I explained you those mathematics for a reason. The reason is, if you see the software is doing something wrong, then you can actually see, you can find the fault there, because you now know the mathematics behind that. So this is how it will look like, and you will inject the phase currents to the relay in order to test your current unbalance pickup. So let's take now a second example of testing, and this example is says if I have a 51P and a 51N element on the same trip contact. What it means is, let's say I have a microprocessor relays, and my processor relay has a trip function which has these 4 elements, which is a under voltage element, an overcurrent, phase overcurrent element, a neutral overcurrent element, and a instantaneous phase overcurrent element. I have these 4 elements for my trip function, and they are associated with the same trip contact. So if, according to the logic, if any of these conditions happen, my trip contact will give a trip, and it will trip the breaker. So how do you test it? Let's bring back Mr. X again, and now he wants to test 51P element and 51NT element. But he sees a problem. What problem it is he sees that my 51N element is getting picked up before my 51P. So he's trying to do like a single phase test, to be more clear. And according to the test, 51N element is getting picked up before 51P all the time. He's not able to test his 51P. There is a reason why 51N pickup is less than 51P pickup in relays, because 51N element is nothing but your neutral overcurrent element, and it is always, the neutral current is very low in magnitude. So I always want to have my neutral overcurrent element to be sensitive for neutral faults or for ground faults. And in that case, I will have a low value of 51N pickup in the relay most of the times when compared to 51P element. So he was not able to do his test because he was doing a single phase test. and he was always failing for that. He was not able to reach the 51P, although he was able to test 51N. So if he had known the concept of symmetrical components, what he could have done is this thing. So let's say he wants to test 51P element first. So what he can do is he can apply only positive sequence current with other sequence quantities to be 0. So why I am showing this is to give you a more good understanding of the use of sequence components. So in this way, what is happening is you're just applying positive sequence current without any negative and zero sequence current. And I told you in my previous slides that negative sequence and zero sequence currents will only be happening in case of unbalanced faults. So unbalanced faults have ground faults and all different kind of other fault conditions. But it is not associated with a three-phase fault and a balanced system. So if I want to test my 51PT element, I will just apply positive sequence current and not any zero sequence current or negative sequence current. If there is no negative sequence or zero sequence current, my 51N element is not getting any current. Why? Because as I explained it, 51N is the neutral overcurrent. It's measuring the neutral flow of current, neutral current. There is no neutral current because I am only supplying positive sequence current. There will be no operation of 51N T element. So I can reach to the conclusion of a path for 51PT. In this example, I'm assuming a 51PT element pickup as 5 amps, just an assumption. You will apply 5 amps positive sequence, as I said, just the positive sequence, and keeping every other quantities to be 0. And then you will reach to the phasor values, because ultimately from a test equipment you are supplying the phase values. So I'm supplying the phase values, and it will give me a 51PT trip. Now he wants to have a test of 51NT element. So 51NT element, in that case, let's do one thing. Let's apply just the zero sequence current. As I clearly explained to you before, that 51NT element is basically measuring the neutral current. And zero sequence current is the one that is flowing through the neutral in case of neutral faults or ground faults. I'm sorry. So if you apply zero sequence current, you will reduce you can test 51NT element. Let's say, for example, I have a pickup of 51N to be 3 amps. You must be wondering why I have this expression 1/3 of 51N pickup. Here it is. Here it is coming from. You remember we derived sequence quantities from phase values. So my zero sequence current was 1/3 of my phase A plus phase B plus phase C current. In case of neutral ground faults, the summation, the vector summation would be equal to neutral current, right? So a neutral current, if I put my 51 neutral current pickup and I supply 1/3 of that, I can do a 51N pickup. In that case, your 51PT element is not getting picked up. Why? Because you're already having a very low pickup, 3 amps, and my phase pickup was already 5 amps, so it will never get picked up. This is how I will do. I will go to the software. I will just write my zero sequence current to be 1 amp, keeping everything 0. And this is how it will look like for the phase values. You will be outputting these phase values into the relay to test that element. That's how you can distinguish between 51PT and 51NT if you have a 3-phase test equipment. Again, because all the sequence components lie with the concept of 3-phase. So you need to have a 3-phase test equipment for that. We do have, as a Mega, we have some protective test equipment which are called as SMRT. that can do all these testing for you. We have the product range is SMRT46D, which is nothing but a 4 voltage channel, 6 current channel unit, and it has a display. And the 410D has a 4 voltage and 10 current channel unit. I was explaining that software will do all the mathematics behind sequence components. So we do have a software like that is called as RTMS, Relay Test Management Software. You can put in all the values in there, and the software will compute all the mathematics behind that and will give you the phasor values in this format, and then you can inject that into the test equipment. I covered talking about transformer differential, time over current, and did not cover distance, but we do have solution for that. If you want to have transformer differential test, we have screens for dedicated screens for them in the software. We have time over current screens where you can see the curves and everything, and the distance screens like that to test those elements. We do have that feature in our software. Going to the conclusions now. Now with the whole presentation, you have understood the whole idea of sequence components, and you have saw that it's a simplified way of performing testing. It will be constant across all the relay manufacturers. Doesn't matter who the relay manufacturer is, because this is a logic or a theory that is being applied across the universe. It's more realistic. It will help you create more realistic fault conditions, and also it is a must-know for fault analysis. If you are a relay settings engineer, you need to know the idea of sequence components. Now I will hand over to Jamie. Okay, I have a question. It says, why does the frequency double during the phase unbalance? Uh, so it's all the mathematics behind that. It's a lot of mathematics behind that, and a lot of studies were done according to that. I have not included that in the slide. It will take much more time for me to explain those concepts. So, but it's a complete different thing that power system study guys did, and they found in that case they are experiencing a double frequency element. That's why it was having a high amount of heating when compared with the normal heating. I have a question here that says the skin effect due to doubling of the frequency causes heating in the rotor. Can we say doubling of frequency causes increased hysteresis and eddy currents, which vary with the same power of frequency? That's true. That's absolutely a different way of understanding the concept. There are so many ways you can deduce to the heating effect. This is the right way of understanding the concept. That's true. Take this example. I have one more question which says, how is equivalent phase time over current pickup calculated in the example with the recloser? So equivalent phase time over current is basically, as I said, it's a line-to-line fault. And for initially, if you don't have, if you're just having like a feeder relay for the phase over current, don't employ the negative sequence component. So you're having a line-to-line fault, which is just measuring the fault current, and usually all the pickups for the phase over current are decided by the fault analysis. Decided by the fault analysis. So the fault analysis will give you the settings. So, and the settings are decided by doing all the different type of faults. So they run all the type of faults, and then they decide what the settings should be. But if I have a negative sequence component, and I showed in the slide, let me, okay. I showed in the slide that the negative sequence overcurrent pickup was √3 times equivalent phase pickup. So you're basically reaching that solution after doing the fault analysis. So that equivalent phase pickup is nothing but, like, let's say, I'm assuming a B to C fault. Can you just go back to the next slide? The one before, I'm sorry. So the equivalent phase time overcurrent curve is basically what it is when you have just a phase B current flowing. But in case of normal setting for the phase overcurrent, you have all the three phases, and for a line-to-line fault, you have like a high value. You have a high value because your B and C phases both are giving the current. So in that, I can say that I have just the B phase current, and that I'm calling it as an equivalent phase. So usually Schweitzer relays, they employ a concept of having like 10%, they just keep a margin of 10% to the downstream relay, and then they compute the value of the equivalent phase pickup, and keeping the time dial constant and a curve shape constant. They are just increasing the pickup. In that way, it will be somewhere between phase time overcurrent curve and downstream phase time overcurrent curve. So they are doing by that. I have not seen this concept in other relays like GE, Basler, but I have seen that in the Schweitzer relays. Okay, I have one more question. It says from Luke, I have a question that says, how does a relay monitor sequence voltages or currents? As you said, the sequence components are not physically existing. They are just a mathematical tool. Is the relay computing the sequence component internally? Yes. The relay is computing the sequence components internally. For example, you said a loss of potential relay picks up on decrease in positive sequence voltage only, and some other relays monitor only negative sequence current. So when testing with Mega software, you enter the sequence values you want, and it calculates what the input should be. So the relay, let me see. So the relay doesn't actually see the sequence values, but the unbalanced and out of phase inputs. That's true. It's absolutely true. So basically, your relay is what the relay is. It's monitoring your voltages, phase voltages, and phase currents. It's not actually monitoring your sequence components. So you need to provide phase values to the relay in order for the relay to internally compute everything. Um, that's how it is done. So yeah, you are absolutely correct on that. Um, I have a question from Matthew. How common is the use of zero sequence current cancellation in transformer differential protection? From what I have seen, a lot of relay manufacturers, microprocessors especially, they employ the concept of that because they don't want their transformer to trip for external faults. So I have seen that being employed in Schweitzer 787 relay, 587, 487, and some of the GE multi-lin 740, some of the GE multi-lin transformer differential relays. So but I have not experienced a wide variety of manufacturing relays till now. So the relays that I have seen, they have the use of zero sequence elimination. The other questions are related with, is there a way we can get a copy of presentation for reference? Yes, you can. Yeah. I have a question here. It says, what's the usual pickup value with respect to the nominal? I don't understand what does it say with respect to the nominal.
It depends on what application they are.
Exactly. Basically, a pickup value, as I said, is computed not from the nominal values, but from the fault values. So they do all the fault analysis, and then they derive a pickup value. So it depends, actually. I'm not sure what do you mean by nominal here. How do you, I have a question which says, how do you filter out all the components? Do you use some kind of signal processing after applying Fourier transform? Yes, that's correct. I have seen that in many microprocessor relays. They do signal processing and then they apply Fourier transformation. So that's correct. In the relay, they are doing like that. I have a question which says, is it customary now to perform only one test for 51P? I have always performed 3 tests by creating a pre-fault balanced system and incrementing one of the 3 phases. Verify 51P for each phase. Best practice. So as I said, it's just an idea of differentiating 51P from 51N. So if you want to do a 51P test, that's the right practice of doing that. You can increment your phasors and you can ramp them up, and then you can check for the pickup value. But there are different kinds of ramps that are being employed for microprocessor relays and for mechanical relays. So it depends on what kind of relay you are using. But that's right, if you just want to verify 51P element pickup, yeah, you can use that. But in a function that I showed where you both have, where you have 51P and 51N elements both on the same trip contact, then yeah, it might be a problem. Then you need to either you can disable the elements, you can go into relay and disable the other element in order to test the element, but that's what not many of the utilities would recommend, because they don't want any change in the settings of the relay by a testing engineer. So they don't recommend changing the settings in the relay or the logic in the relay and then again changing it back to the original condition. So if you are not allowed to do that, then you need to follow the sequence component idea. I can see when you waiting for more questions now. I cannot see more questions here. We do have time. If you have a question, just type in there and I will be more than happy to answer that. Okay, I saw a question here. As shown, VB is actually VC as shown. Okay, you have answered it. Perfect. So this has been answered.
If you have answered everything, then
Yeah, now I will hand over to Jamie and we can take care of all the rest questions. Just type in there and we will answer all the other questions offline through emails. So I will answer all the questions when I get a chance. I will go across each and every question which I've just missed in here and I will send in the emails to you guys. Now I'm handing over to Jamie again.
Okay, it looks like we're out of questions for right now. Like you said, if you have any other questions, feel free to contact us offline. You can just email them to me directly, actually, at jamie.smith, that's jamie.smith@megger.com, and I'll forward those questions over to the correct person, and we'll get back to you as soon as possible. But that's it for today. Thank you all for attending. We hope to see you again at our next webinar. Have a great weekend, and also remember to answer the survey if you can. We'd really appreciate it. Thank you.